A pendulum is a mass suspended from a pivot point that swings back and forth in oscillatory motion. When set in motion, inertia drives the mass past its equilibrium position, and the restoring force due to gravity drives the mass back to its equilibrium position, and so on. The distance from the equilibrium position to the maxima is called amplitude. Period is the time required to complete one oscillation, and frequency is the number of oscillations completed in 1 second. We have decided to focus on the frequency aspect of a pendulum for our project. Anything that hangs from a focal point and swings in an arc provides a picture of pendulum applications, such as swings. Pendulums have been historically involved in clocks, grandfather clocks in particular, predicting earthquakes through seismometers, and architecture through designing buildings to sway with ground shifting. With that being said, let's hop into the concept. According to the frequency of a pendulum equation, the length of the string is the only variable that affects frequency, as acceleration due to gravity is a constant. With that being said, the frequency of a pendulum is not affected by amplitude nor mass, but rather by the length of the string. We tested the effect of three different variables, amplitude, mass, and strength length, on the frequency of a pendulum, conducting tests where the variable of interest was changed and the other two remained constant. This was based on the hypothesis that increasing the length of the string would cause a decrease in frequency, while alternating the other variables would not cause a significant change. For the amplitude test, mass and strength length were constant, while amplitude was changed using the shown measure tapes. For all three tests, the motion of each of the three trials was analyzed through the video analysis app. The expected frequency was calculated through the equation, and the observed frequencies were obtained from the motion graph. Here's a sample graph from a trial of the amplitude test showing how frequency was calculated. From looking at the graph, the time required to complete one oscillation, period, was found, and frequency was obtained as a result. As predicted, the observed frequencies were insignificantly different across the three trials of the amplitude test, regardless of the change in amplitude. For the mass test, amplitude and strength length were constant, with only the mass being changed. Here's also a sample motion graph of a trial from the mass test. As predicted, the observed frequencies were also insignificantly different across the three trials of the mass test, regardless of the mass change. For the final test, strength length was a variable changed, while mass and amplitude were remained constant. A motion graph of one of the trials is shown, describing how the observed frequency was identified. However, this time, the observed frequency was significantly different every trial as the strength length was changing, in contrast to the amplitude and mass tests. The frequency decreased with every increase in the strength length. To conclude, the strength length experiment was the only demonstration that presented changing frequencies in response to the changing independent variable, indicating that strength length, in fact, is the only variable that influences the frequency of a pendulum. This confirms our starting statement that the frequency of a pendulum is not affected by amplitude nor mass, but rather by the length of the string. The data of the strength length test also supported our hypothesis that increasing the strength length decreases the frequency of a pendulum.